Hello, everybody. This week, week 7, we're looking at chapter 6. Talking about the standard normal curve, but we're going to talk also a little bit about general continuous probability distributions. So, the things for this chapter, we are going to talk about probability density curves for continuous distributions. We're going to talk a lot about the normal curve and the normal population, and then the meaning of the areas under a curve and how to find the areas under a curve. And then, of course, z-scores. Let's start out talking about population and probability density curves and how those work. Now, if you'll recall, when we talked about discrete distributions and talked about just data distributions in general, we talked about having that number line and just pretend that goes straight across there. And everything's numbered out. Every time there's a value, we put a dot above that value, and those dots kind of formed a shape, and we drew that curve over the top of that shape. So then you drew the curve over the top of all those points and it formed a distribution. Well, now, since this is a continuous distribution, we don't have those individual points. The values can be anywhere in between rather than above the certain numbers. So we can have points at any possible point along there. So what we end up with is a continuous density curve like this. You can see we're relating it back to that frequency histogram. But rather than having classes, those class widths can get smaller and smaller and smaller. So those bars get narrow and narrow, like you can see in the second drawing. And basically they get infinitely small. In other words, they get so narrow they have no width. And that's what the continuous distribution is. And so what that means is each value, the height of the curve is still how likely it is for that value to occur. But each value above its value is just a single line that has no width, so that has no area. And the probability is defined as the area under that curve. So the area under that curve has to add up to 1, because remember from our discrete distributions, a valid probability distribution, all the probabilities have to add up to 1. And the area of being... So when we're dealing with when we're dealing with continuous distributions, we can't be looking at the probability of a single value. We have to be looking at the probability of a range of values. And the probability of that range is the area. Let's say I want to know the probability of it being, for this distribution, between 1 and 2. So there's 1 and there's 2. So the probability of being between those two values is the area under the curve between those two values. So this is our probability density curve. And that is how we find probabilities from that curve. So like here, they're explaining the area under that curve between two values, A and B. Here we're going from 3 to 4 is the probability of, let's shrink this up a little bit. There we go. Is the probability of being between those two values. So here, again, probability of being between 3 and 4 is that area there in gray. So what this represents is the probability that if I randomly select any of the possible values for that variable, that value that I finally select will be between 3 and 4, between those two values. So here we've got this diagram for our density function. What is the proportion of the population that's between 4 and 6? So there's two different ways you can describe it. That area is describing the proportion of the whole population that is between those values. It's also describing, if I randomly select a value, or I randomly select an item from the population, the probability that that item will have a value in that range. So here, looking at this, portion of the population between 4 and 6 is equal to the area under the curve between 4 and 6. And of course, that is labeled as 0.16 is that area. If a value is chosen at random from this population, what is the probability to be between 4 and 6? Well, you can see it's still between 4 and 6 would be 0.16. This is probably not being between 4 and 6. Well, that would be the complement. Remember, the whole distribution adds up to 1. So if this here is 0.16, everything else adds up to 1 minus 0.16, or 0.84. So the region above a single point has 0 width. That's like I said, if a single value, it has 0 width. It's got a height of the curve, which still is displaying, how likely, the higher it is, the more likely that value is to occur, but it has 0 probability of itself because it has no width. So because this is continuous, we are always looking at ranges, and it's always going to be put in terms of the probability that our value x is between a and b. So it's between a lower limit and an upper limit. So a is what we call a lower limit, and b is what we call an upper limit. Now, because the probability of being equal to a is 0, it doesn't matter whether we have this as strictly less than or if we have it less than or equal to, because the equal to has 0 probability, so it doesn't change your probability at all. As we look at these probabilities, of course, most of what we're going to do is we're going to be looking at a range like this. And when we enter it in the calculator, all our probabilities will be a range between a lower limit and an upper limit. But what if I wanted to ask the probability that x is just less than a value, we'll call it b. Well, what that is saying is on that curve, if we have a value b here, we're saying everything that is less than that value. What is the lower limit? Well, there might be a value here that all values are greater than, but we're guaranteed that negative infinity is smaller. Oh, my handwriting is horrible here, so I'll try that again. That negative infinity is smaller than any of the values. So what we do is we put that in as probability of x being less than a value is the probability of negative infinity being less than x being less than the value that we are looking at. And then we do the same thing if we're asking the probability that x is greater than a value. It's going to be the probability that x, that value is less than x, is less than a positive infinity. So now the question is, when we look at the calculator, how do we enter negative infinity and positive infinity into our calculator? And we're going to look at that in our next section here as we move on to describe normal probabilities in the normal curve. We're talking about the normal curve, normal probabilities. We're going to start talking about standard normal. Excuse me. The standard normal curve doesn't show up there. So standard normal curve has a mean of 0. Remember back to our empirical rule, the mean is the center of the curve. And a standard deviation of 1. So this is -1, -2, -3. +1, +2, +3. And you got those percents in there. Now, the percents that we got from our empirical rule are actually just normal probabilities. They're rounded slightly. As you can see here, this was 68. If we actually use the normal probabilities, we'd get like 68.27, something like that, percent. But anyway, that is how this all starts. The standard normal curve has that value. Basically what you see here is these are z-scores. 1 standard deviation above the mean would have a z-score of 1. 2 standard deviations above the mean would have a z-score of 2. 2 standard deviations below the mean would have a z-score of -2. So our values end up being z-scores. So when we're dealing with standard normal, we're looking at the probability of A being less than Z being less than B. It's going to have Z in there. We're actually looking for the probability of Z. It's a distribution of Z. We're going to look at applying the normal probabilities to real life examples and applications. In that case, then it's going to be X in there. And then we're going to be putting in our actual mean and going up and down by the standard deviations here. So we'll look at those as we get to it. So the probability density curve comes in many varieties. This is our normal curve. Normal distribution is that bell curve, and it is the distribution that much of our data in nature normally takes on. So now we explored this a little bit when we talked about z-scores. Here we can have a normal curve. These both have a mean of 0 because the center here is at 0. This first one has a standard deviation of 1. Second one has a standard deviation of 2. You can see it's much wider, the dotted curve. Over here, this is a standard normal curve here. We've got the mean at 0, standard deviation of 1. This one, the dotted curve, still has a standard deviation of 1, but the mean is 5 instead of 0, so it shifts it side to side. So changing the mean, as we can see here, shifts it side to side. changing the standard deviation makes the curve wider or narrower. Normal distributions obviously have one mode. They are symmetrical. So if I found the probability of being at the center here, this is the mean, remember. The probability of being less than has to be equal to the probability of being greater than, which means each side has a probability of 0.5 or 50% if you're looking at it as percents. Mean, median, and mode are all the same value, and they're exactly at the center. So that's not just the mean, it's the median, and it's the mode. This is, again, our empirical rule that we looked at. Oops. And what we'll find when we start looking at our probabilities is that these percents, as I said, are approximations. They're rounded off probabilities from our normal distribution. So now let's actually look at the standard normal curve. Now by standard normal, remember, that is the mean equals 0 and the standard deviation equals 1. So in our bell curve, the center is 0, negative 1, negative 2, negative 3, positive 1, positive 2, positive 3, as I showed you before. So mean is 0, standard deviation of 1. So we're looking at Z is our test statistic, or not our test statistic, but our statistic is Z that we're looking at, our value of interest. So here, this is our curve, and as again, Z is the value we're going to be looking at. So if I want to find the probability of being less than Z, or the proportion of the population. Remember, this shows two things. One, it shows the proportion of the population that is in that range. So this would be less than the value Z. Or the probability that a randomly selected value, a randomly selected item, will have a value in that range. So it would have a value less than Z in this case. Now, if you're using the Z table, like a probability table, like there's one given in your book. It's in a kind of a heavier card. Might even be laminated in the new books. That Z table always gives you the probability of being less than the Z score that is given. So you look up the Z score in the table. You have to use Z scores in that table. You look up the Z score. The probability that's given in the table is probability of being less. Now, we have the calculator to us. I mean, if this would have been 7 or 8 years ago, we would have gone through that table in detail on how you use the table to find probability of being greater than or probability of being between. We don't have to worry about that now because we have the calculator available to us. This here is showing you that table and how it works. I mean, this is a Z score of 0, 0.3, whatever. This is 0.34. 0.34 be the Z score. This is 0.3, and this is the hundredths digit on the end. Probability that Z is less than that is 0.6331. Now, again, you don't necessarily have to be able to read this table. I spent a lot of time when I was younger reading these tables because we didn't have the TI calculator at that point. Right now, the TI calculator calculates probabilities better than Excel can. So we're going to use, for this course, we're going to lean on that calculator. And in the TI calculator, you go to the distributions menu again, that's second distributions, and normal CDF. We will never use normal PDF. What normal PDF would give you, put in normal PDF, it's just going to give you the height of the curve at that value. Well, the height of the curve is not a probability. It's an area for probability. That area would be 0. So we are always going to use normal CDF for finding probabilities. So option 2. Inverse normal is going to be used if we know the probability and we want to find the corresponding Z-score, or if we use, put in more information, the corresponding data value that corresponds to that. So on a calculator, this is going to be second. Distribution is right here above variables key. You can see option 2 there, normal CDF. So Clear that out. So let's look at some examples here. We're not going to use the table. We're going to use the calculator. But find the area to the left of 1.26. So you can see from the diagram they gave you, the left of 1.26. Finding the area to the left of that, basically asking what is the probability that z is less than 1.26. Okay, now if you use the calculator, if you have the newer version of the TI-84, the TI-84C I believe it is, it uses something called the stat wizard. When you call up normal CDF, it would go to a stat wizard. My calculator, I have this one set to be the older version in case you don't have it. It just brings up normal CDF and you have to enter the information in yourself. If you want to see the stat wizard, I used the stat wizard on Friday night when I did my weekly online office hours. So you can go and look at that and go into the meet on the website and go to the recorded session from Friday, and I'll show you how the stat wizard works. But here, probability that z is less than 1.26, that's basically asking what's the probability negative infinity is less than z is less than 1.26. Because remember, we have to have a lower limit and an upper limit. So the upper limit, if we're less than 1.26, our lower limit would be negative infinity. Anything from negative infinity up to 1.26 is less than 1.26. How do we enter negative infinity in our calculator? Well, there's one of two ways. The calculator takes negative infinity as a negative sign. Remember, negative is not minus. This is the negative sign down here. Followed by 6 nines. The calculator recognizes that as negative infinity. So it's 6 nines in a row after the negative. Also, the calculator recognizes negative 1 EE99. That's negative 1 times 10 to the 99th is what that's saying. So it's a negative 1 followed by 99 zeros. So on the calculator, we can enter it either way. I'm assuming you guys can do the negative and enter the 999999. So I'm going to show you how to do the negative 1 E99, which is actually how your textbook does it. So negative 1, put in the 1. Now we're going to do second. Now, it's not the letter E, it's actually this one here, EE for scientific notation. It only puts one E there, but it's actually an EE key that we're putting in, and 99 is the number. Comma, we're going up to 1.26. Now, normally here, if we had anything other than a standard normal curve, we'd put in another comma, we'd put in our mean, then we'd put in another comma and put in our standard deviation. I could put in comma 0, comma 1 here. 0 would be the mean, 1 would be the standard deviation. But if I just leave it there and I close my parentheses, the calculator will assume that there's a mean of 0 and a standard deviation of 1. Hit enter. That's going to give me 0.8962 if I round it off. If I look back here on the table, that's what it would give me, 0.8962. Because remember, the table does give you the probability of being less. And so I'm going to stop talking much about the table because we don't need to know how to use it if you got the calculator. And this is showing you the calculator how to enter it. Negative 1 E99 is the negative infinity. 1.26. Now they did enter the 1 or 0 for the mean and 1 for the standard deviation. Notice I did not enter that, and the calculator still did it. The calculator just assumes those. You don't have to enter those in if it's 0 and 1. So now this one, it's saying find the area to the right. So the area to the right of negative 0.58, that's saying probability that z is greater than negative 0.58. So the area to the right of that. So again, what we could do is we could look this up in the table. Now this is going to probability less, so we'd have to do complement 1 minus to get the probability. Again, we're not worried so much about the table. So on the calculator, the probability of being greater than a value is the probability that that value, negative 0.58, is less than z and less than infinity, positive infinity, or just infinity. So what this is saying is z is between negative 0.58 and infinity. Obviously, somewhere up here is positive infinity. We're between negative 0.58 and that value. So on the calculator, second, distribution, normal CDF. We're going to put the negative. Remember, you got to use this key for the negative. You can't use the minus key. 0.58, comma. For positive infinity, 1 second EE 99. Now again, I could have done, for a positive infinity, I could have just done 6 nines. The calculator will recognize that as well. This textbook wants to use the 1 EE. And remember that EE is not the letter E that you find up here with the alpha. It's the second EE for the scientific notation here. I could put in the comma 0, comma 1, but I don't have to. The calculator will assume that if I don't enter it. It's going to give me 0.7190, which is what they got from subtracting on the table. Of course, the next window here should show us that calculation. It's the complement 1 minus what we got out of the table. Again, in the calculator, just enter it from that value, negative 0.58, positive infinity, the 1 E99. Again, they entered the 0 and the 1. You don't have to. The calculator will assume that. If you want to be safe, you can always enter it. And in fact, if you use the stat wizard, what's going to happen when you enter normal CDF and you hit enter to select it, what it's going to do is it's going to go to a window. It's going to have lower limit, something like that. It's going to deliver lower limit, upper limit, mean, standard deviation. In the stat wizard, you may have to put in 0 and 1 here, because if there's other values have been used, those other values will still be in there for the mean and standard deviation. So you have to put in the 0 and 1 to make sure you cancel those out. And of course, negative 0.58 and the 1 EE99. Or I prefer to just use the 6 nines, 999,999. And that's positive infinity. Just the nines is easier for me because I don't have to remember how to get in the scientific notation. Now it's saying find the area between negative 1.45 and 0.42. So this is P, the negative 1.45 is less than Z is less than 0.42. This one's easy to put into the calculator because we don't have to, put in a positive infinity or negative infinity, because we have both endpoints. We have both the lower limit and the upper limit. Here's our lower limit. Here's our upper limit. Now, if we were using the table, we would look up both values and do some subtracting. We're not going to worry about that. Let's worry about, see they're doing the table here. Let's worry about entering this in the calculator. So again, second distribution, normal CDF, negative, remember to use the negative key, not the minus, 1.45, comma, 0.42, close parentheses, and enter. So 0.5892, that's what they're getting here. 0.5893 they're getting. It looks like 92 to me. So anyway, let's go see what they got off the calculator. They're getting the same thing we did, 0.5892. So that's just a rounding error. And if we use the table, we got a little bit of rounding error, puts us off by a 10,000th down there. But you can see their command in the calculator here is exactly what I just did. Only I chose not to put in the 0 and 1 because the calculator will assume them. So that's standard normal using z-scores. If we don't have standard, we're not looking at standard normal distribution, we have two options. We can first find the z-score for every value. So we can convert every value into a z-score. So remember, that's taking the value x, subtracting the mean, and dividing by the standard deviation. And if we turn every value into the z-scores, then everything's going to work just like it just did for our standard normal. That z-score basically has converted it to a distribution with a mean of 0 and a standard deviation of 1. If you're using the table, you have to do that. So that's why we're going to kind of skim through the table here and not look at it so much. Because I want to show you the calculator so you don't have to worry about the z-scores for that. So they're talking here about finding those z-scores so you can use the table. We don't have to worry about that. You can use the inverse normal. They're talking about inversing here. Okay. They're going to use the inverse normal. If you know a probability and you want to find what value corresponds to it, we can do that as well. So it looks like what we're going to be doing in this section actually is if we know a probability, finding the z-score that corresponds to it. So let's take a peek at that. And the inverse normal command on the calculator is what is going to allow us to do that. What that is saying, the inverse normal command, what you're going to be looking at is on a curve here. If we put in the probability, the area under the curve here, it'll tell us what value is at this end here. This is that z-score, that value. So we put in this area, and it tells us what z-score, what value is above it. So that area, if it's that area, it'll give us this z-score. If it's this area, it'll give us this z-score here, which is what the table will do. And if you're using the table, you'd have to read it backwards. If you knew the probability, you have to find the value in the table here that's as close to the probabilities you can find. Saying if the area to the left is 0.26, if this area is 0.26, you'd find that probability here. 0.2611 is the closest value to 0.26. That is negative 0.64. Again, we're not going to use using the table for that. You can see I'm rounding because it's not exactly 0.26 here. So I'm looking for a more exact answer from using the calculator. So on the calculator, I got to remember the calculator only uses that probability if it's less than the z-score. And here it is. That probability is less than the value I'm looking for. So I can use the calculator. On the calculator, I'm just going to type in second distribution. Option 3 is inverse normal. I'm putting that probability of 0.26. Now I could do, notice they're putting in comma 0, comma 1. That's to tell the calculator that's the standard normal. If you don't put it in, the calculator just assumes. So that's going to give me a negative 0.6433, exactly what they got here. So that is saying a z-score of negative 0.6433 corresponds to that probability. This again is using the table. If I want to find the value that has an area of 0.68 to the right of it, well, what we're going to do is we're going to do this. For the calculator, if I want to know what value has 0.68 to the right of it, this is symmetrical and the whole thing adds up to 1. So the part that's less than it would be 1 minus 0.68 or 0.32. So what I'm going to be looking up on the calculator is 0.32. Second distribution, inverse normal, put 0.32. And again, I didn't put in the 0 and 1. The calculator just assumes it. We get the negative 0.4677, basically, if I round it. The next possible way we can look for z-scores from probabilities is, let's say we want to know what z-scores bind or are the bounds for the middle 95% of the data. This is a common question that comes up on that group worksheet for z-scores. What we're looking at here is binds the middle 95% of the data. So that means we're looking at finding 95% in the center of this bell curve. Well, there's 95% inside this shaded region. That means there's 5% outside. And since this is symmetrical, that 5% gets split evenly to be 2.5% on either side. So now if I'm looking at this, if I want to find this point here, I need this area. Well, that area is the 2.5% or 0.025. If I want to find this value here, I need this whole area. Well, this whole area is 100% minus 2.5%. In other words, 97.5%, or a probability of 0.975. So on the calculator, second distribution, inverse normal, 0.025. Notice I don't even need to close the parentheses. it's going to give me a negative 1.96 basically. So this value here is a negative 1.96. If I do this one, second distribution, inverse normal, and I put in the 0.975, I get positive 1.96. It makes sense. Since we're taking this out of the middle, we are getting the z-score should be the same. It should be symmetrical, one negative, one positive on each side. And that's exactly what they found in their example here. Now another one I want to do, I'm going to throw it in here in just a second. Yeah, that's like we're going to do it here. So in table A2, find the area. Yeah, they're reversing all that. This is the calculator again, putting in each of the values. They just put in the lower one, the 0.025, and found that. And because you know it's symmetrical, you know the upper value is going to be the same. So once you find this one and know that this is a negative 1.96, you know this one has to be a positive 1.96 because it's symmetrical. Now the one thing I want to find, I'm going to do this on this next page because there's a little bit of room here. Let's say I want to find the 65th percentile. What that is saying is, under my bell curve, what value here has 65% of the data less than it? In other words, this is a 0.65 probability. That area is 0.65. So I can just do the calculator, second, distribution, inverse normal, 0.65. It's going to give me a z-score of 0.3853, or 0.339 is the z-score. So the z-score of 0.39 is at the 65th percentile. Now this will make a lot more sense. There's a lot more useful calculation if we have numbers in there, real means and standard deviations instead of the standard normal. But you can see how we can find that that's just a probability. It's the percentile is just the probability of being to the left of that value. Okay, let's get back to the slide here. Let alpha be any number between 0 and 1. So that's a probability. Between 0 and 1 is a probability. The notation z alpha refers to the z-score with an area of alpha to its right. So z alpha means that this is the z-score that has this area of alpha. That's what that means. And here's their picture illustrating that. So z of 0.2 is this z-score here. It has an area of 0.2 in here. That comes out to be 0.84 is that z-score. Now remember, you'd look that up. If that's 0.2, this area is 0.8, because 1 minus 0.2. So you put in the calculator, it's going to be the inverse, second distribution, inverse norm, 0.8 is what we're going to put in there. It'll give us the 0.84. So this is doing it with the calculator, which we just did. So we got the 0.84, 1621. So in summary, what we looked at here was the regular continuous probability distributions, probability density curves. And then we looked at the standard normal distributions, finding the probabilities for z-scores and finding the z-scores that correspond to certain probabilities or areas under the curve. In the next section, we're going to be looking at, as I was mentioning, when we actually get means that are not 0 and standard deviations that are not 1. So we're going to go to the PowerPoint for 6.2. So I'm going to pause a second while I switch the PowerPoints. Okay, so we've talked about the standard normal curve and z-scores. Now we're going to look at the applications of the normal distribution. So now for these, our mean is no longer going to be 0, and our standard deviation is no longer going to be 1. And this is, as I had mentioned before, one of our options is going to be to convert all of our values into z-scores. If we wanted to use the table, we would have to do that. We've got the calculator now, so we don't have to do that. Then we can find our area under the curve. We can also find the value, the actual data value from a probability or a percent by finding the z-score and converting it up. Again, the calculator will do that conversion for us. So we're going to start convert values from a normal distribution to a z-scores. So this would be, we've done z-scores before. So all a z-score is, as you can see here, is the value minus the mean divided by the standard deviation. So the example, just to review z-scores, heights of a certain population of women follow a normal distribution with a mean of 64 inches, standard deviation of 3. Randomly selected woman has a height of 67 inches. The z-score is just the value of 67 minus the mean of 64 divided by 3, which is a positive 1. And that's what they're showing down here in their calculation, getting the positive 1. Now, if we want to do probabilities based on that, we could throw that into the calculator based on whatever probability we're trying to find. So finding areas under a normal curve. Now notice it's not standard normal, just normal. So it's any normal curve that has any mean or any standard deviation. So when using the tables, we have to find the z-score first, as I mentioned. We're going to kind of skim through that a bit because we're going to use the calculator. So I said you find the z-score and then use the methods we did for the standard normal curve. So here, a study reports that the length of pregnancy of conception to birth is approximately normally distributed with a mean of 272, standard deviation of 9. What proportion of pregnancies last longer than 280 days? In other words, the probability that a randomly selected pregnancy is greater than or equal to 280. Greater than or greater than or equal to, remember, it doesn't make a difference because the or equal to has 0 probability. Notice I'm using x here instead of z because this is an actual data value, not a z-score. I could find the z-score, and the PowerPoint here is going to go through finding the z-score in a second. But I can also just do this in the calculator. This is the probability of x being between 280 and positive infinity. So I can do the, so on the calculator here, second distribution. This is normal CDF. My lower limit is the 280, comma. Upper limit's positive infinity. So 1 second EE 99 is my positive infinity. Notice I did put in the comma here. I'm not using standard normal anymore, so I do have to enter my mean and standard deviation. My mean is 272, and my standard deviation is 9. So I put in my end my parentheses in my command there, and I get 0.1870. Now if I'd found the z-score there, I'm going to get a really ugly z-score. I believe it's 0.888, something like that, 0.89 if I round it. Look that up in the table. We have to do, remember, a 1 minus with the table. Because the table is going to give us the probability of being less than that z-score. We subtract from 1 to get the greater than. Again, like I said, I'm skimming. I know I'm skimming through the table real fast, but we're not going to use the table for this course. Since we are interested in the proportion of pregnancies lasting longer than 280 days, it's to the right of that, so we had to subtract it from 1. Here's our calculator command. This is exactly what I just put in. Notice they put in the mean and standard deviation as well. I got the 0.1870 as I did. So here's same situation. Pregnancies has a mean of 272, standard deviation of 9, but now they're asking for it to be considered full term is between 252 and 298. So what proportion of pregnancies, or what is the probability that a randomly selected pregnancy will be full term? In other words, what is the probability that x is between 252 and 298? Well, we've got our lower limit and our upper limit, so this should be easy to put in the calculator. Second distribution, normal CDF, 252, comma, oops, 252, not 0. 252, comma, 298, comma, I do still have to put in my mean, 272, comma, and standard deviation of 9. Now, if you're doing the stat wizard, the mean and standard deviation would still be in there from the last problem. But we're going to enter here since we're using the brute force command. So I get 0.9849 is the probability of being in between here. So they notice what they did here is they converted each of them into z-scores, and they're going to look them up in the table and subtract the two probabilities from the table. So actually, yeah, the two probabilities, and they subtracted them. They did get 9849, which is exactly what I got up here. Showing it on the calculator, they got the exact same command and the exact same probability as I did. So that is if you want to know the probability of being between 2 points. All you got to do is add in the mean and standard deviation to your command. So if we want to go the other way, if we know the probability or the area in the normal distribution, we want to find the given value. So suppose we want to find the value from a normal distribution that has a given z-score. We can find the z-score. We've already done that. But let's say we want to find the actual value. So here, heights in a group of men are normally distributed with a mean of 69, a standard deviation of 3. Find the height whose z-score is 0.6. So if we know the z-score and we want to find the height, well, remember z equals the value minus the mean, so that'd be minus 69 over the standard deviation, which would be 3. If the z-score is 0.6, you put 0.6 in here. So we're going to multiply 0.6 by 3 and then add the 69. So right there. 0.6 is multiplied by 3 and then added to 69 gives us 70.8. Now again, this is if we're using the table and we had a certain probability. The table is going to give us a z-score. We have to be able to convert that z-score into a data value. With the calculator is going to automatically give us a data value, so we don't have to deal with that. So use this procedure to find a value from the normal distribution as that proportion above or below, or bracket it like we did where we found that have the 95% in the middle. We might look for finding percentiles. We'll look at those too. So we'll get back to that here in just a little bit. So again, I'm going to skip over the table stuff here, and I'm just going to do the calculator commands on this. So Mensa organization is members who's limited to those whose IQ scores in the top 2% of the nation. So in other words, this probability is 2%. So 0.02 would be 2%. IQ tests have a mean of 100 and a standard deviation of 15. What is the minimum score needed? So we need to find this value, x. Now what we could do is find the z-score using the table and convert that z-score into an x value. We're not going to do that. We're just going to use the inverse normal command on the calculator. What probability are we going to put in there? Well, we need the probability that's on this side of the curve. If this is 0.02, this probability would be 0.98 because the whole thing adds up to 1. So 0.98. So remember, just the probability, and then we're going to put in the mean, which is 100, standard deviation of 15. So in the inverse normal, we don't have an upper limit and a lower limit. We just have the probability. So here we're going to put in second distribution, inverse normal, 0.98, comma, 100, comma, 15. Enter. 130.81, basically. Now, in this next slide, they're going to be using the table, so they're going to find the z-score. Well, they're just explaining why you put in the 0.98 instead of 0.02, which I already explained, because this area over here is what we're finding is what the calculator uses and the table uses is the area to the left. The 0.02 is the area to the right of our desired value. So we use the complement to the 0.98 is the area to the left. They use the table to get a z-score. To find this is the probability closest to 0.98. Found a z-score of 2.05. they converted that z-score into a value, 130.75. We used the calculator, so we didn't need that, and it gave us the exact same thing I did, 130.81 if we round that off to 2 decimal places. So what we saw on this PowerPoint is converting values to z-scores, finding areas under the curve, and finding the value from that area under the curve. I'm going to do some more examples here quick for us, just because I don't think what we just did was quite adequate. I'm going to give myself some blank pages to work with. Okay, so what I want to do is, let's say that we are given that on our next test, on test 2, throughout all the years that test 2 has been given, there's a mean score of 77 and a standard deviation of 8. So what we want to find to do is, what is the probability that a randomly selected student will score, let's say we're asking between 70 and 80. So we're going to focus on the calculator here. So we got lower limit of 70, upper limit of 80. So going to the calculator, second distribution, normal CDF, lower limit of 70, upper limit of 80, comma. Our mean is 77. Standard deviation is 8. Hit enter. 0.4554 actually, is the probability that a randomly selected student is going to score in that range. Or the other way you could look at it is the proportion of the population that scores between 70 and 80 is 0.4554 as well. If you want to do a percent, it'd be 45.54%. How about probability that randomly selected student scores less than 75? Now again, because this is a continuous distribution, it doesn't matter whether it's less than 75 or no more than 75 or less than or equal to 75, because the or equal to has 0 probability to it, so it doesn't change things. Less than 75 means we're finding a value that is between 75 and a negative infinity. So second distribution, normal CDF, negative infinity, I'll use -1, second EE99, comma. 75 is my upper limit. My mean is still 77. My standard deviation is still 8. Gives me 0.4013 is the probability that a randomly selected student will score below 75. Or that's the proportion of the population that scores below 75 is 40.13%, or 0.4013 proportion. How about we find the probability that randomly selected student has a score greater than 80. So again, this is greater than, I'm just going to put it right in the calculator. Second distribution, normal CDF. 80 would be the lower limit. If it's greater than, the upper limit would be positive infinity. So 1 E, remember I'm using the comma here, second comma for E, 99. Mean is 77, standard deviation of 8 still. Close, enter. 0.3538. So that's how we can find those probabilities. Now I want to go the other direction. So we did here, the probability being between two values, we just entered normal CDF, put in those values, 70 to 80. We had our mean, and we had our standard deviation. Less than, there's normal CDF. It was negative infinity, -1, E99, so I put in negative infinity. Our upper limit was 75, mean is 77, standard deviation of 8. Greater than, normal CDF. The 80 is now our lower limit. Our upper limit is now positive infinity, so 1 E99. Mean is 77, standard deviation of 8. So the next thing I want to look at is what if we have, we know the probabilities and we want to find what z-score or what test score actually corresponds to that. So I'm going to bring this down here. We're still going to use these numbers. So that next test, we still have historically a mean score of 77, a standard deviation of 8. What I want to know what score represents the 90th percentile. So on my curve, the 90th percentile is the spot here, the value that has 90% of the data less than it. So in other words, that probability is 0.9 for 90%, 0.90. So what I'm going to do here is I'm going to do an inverse normal. My probability is 0.90 or 0.9, and I have to enter the mean of 77 and 8. So second distribution, inverse normal. 0.9, comma, mean is 77, standard deviation of 8, gives us 87.25. So the 90th percentile is 87.25. Now we had mentioned when we did percentiles by hand before, it was either, the percentile was either a data value or in between two data values. That was because we had a discrete number. We had a limited number of data values. Here, this is a continuous distribution, so we don't have individual values. So literally any value in between numbers can be a data value. So 87.25 actually could be, it is one of our data values because every value in between is also in the data set. Let's say I want to know what score is less than 40% of the class. So in other words, in my curve, what score here will have 40% greater than it. What score is less than 40% of the class. So our inverse normal on the calculator only does the area to the left. So this area is 1 minus 0.4 or 0.6 for that area. 40% of course is a 0.4 probability. So we are going to do inverse normal. I'll put in the 0.6. The mean is 77, standard deviation of 8. Inverse normal, 0.6, 77, 8. 79.03. So this is 79.03 is that data value. So that is 79.03 has 40% of the data greater than it. Or 40% of the students will score better than 79.03. Might ask what values bind 60% of the data in the middle. Or what values bind the middle of 60% of the data might be another way of looking at it. Here's our bell curve. We're focusing on 60% in the middle here, which of course is a probability of 0.6. There's 60% inside our area here. That means there's 40% outside. And since this is symmetrical, that splits at 20% less than and 20% greater than. So this has a probability of 0.2. This has a probability of 0.2. But remember, we're looking at the probability to the left, so this would correspond to 0.2 here, because that is to the left. This is not going to correspond to 0.2. It's going to correspond to 1 minus 0.2, or 0.8. Now notice between 0.2 and 0.8 is 0.6, so that is our 60%. So now we have to do an inverse normal to find the 20th percentile, or 0.2. Second distribution, inverse normal, 0.2, comma, 77, comma, 8. I'm going to purposely forget my parentheses, close my parentheses, and it still works out. So 70.27 is that value. Over here for the 0.8, second distribution, inverse normal, 0.8, comma, 77, comma, 8. I'll close my parentheses this time just to for good form. 83.73 is this value. Now one thing you'll notice, the mean, if you recall, was 77. The difference between the mean and the 70.27 is 6.73. The difference between here is also 6.73. These values should be equidistant from the mean. In other words, the same difference between the mean on either side. That's pretty much it for this chapter. So we went over some examples also in our recorded meet session from Friday night. So there might be some other examples there for you that are helpful. But that is basically the standard normal curve and then the applied normal curve. Remember, whenever you see standard normal curve, we're talking about the z-scores. So mean is 0, standard deviation is 1. But the applied normal curve, we can change that mean and standard deviation to anything like we did here. Change the mean and standard deviation and just let the calculator automatically do the z-scores for us. Like I said, the book goes over just finding the z-scores and using the table, but we don't have to use the table anymore now with the calculator. Okay, that is pretty, like I said, that is it for this week. If you have any questions, let me know. I'll get back to you as soon as I can. Otherwise, you have a great week.